Hello, everyone. My name is Abhishek. I'm a senior product manager on Amazon Athena. Thank you for choosing this session amongst probably 50 other very interesting sessions. We appreciate that. We're going to take a deep dive on Athena, and hopefully my aim is, after the session, you might say, well, that didn't sound too hard, because the core principle of what we've built Athena on is simplicity, that we want to hide as much complexity as possible when it comes to building a big data system. And that's predominantly what Athena is built on. We also have the privilege of welcoming a customer who is going to talk about their use case and their journey of using Athena all the way from Rio. So we have Raul from OLX Brazil. OLX is an online marketplace, and they'll talk about how they have used Athena in conjunction with a bunch of other tools, and what do they like and what do they not like about the tool. So let's get started. So we'll do, there's a lot of topics here, so I'll go really quickly. Hopefully they're all very simple things to understand at the end of it. So we launched about a year ago, so tomorrow is actually our happy birthday. So Andy Jassy launched our service last year at Keynote. So we've had a pretty busy year. Since our launch, we have added multiple ways to connect to Athena. For example, we've added an asynchronous REST API that you can use various different SDKs to talk to Athena. It's a query API. We added support for AWS CloudTrail. That means you can audit every query that goes through the system. We added support for JDBC and ODBC drivers, and there have been a bunch of new versions of those drivers that have been out there. We've expanded to 11 public AWS regions. We've added support for Grok, Geospatial Data, and using and Avro formats. We also added support for processing data using encrypted data using server-side encryption or client-side encryption with keys in a KMS. We integrated with AWS Glue and AWS Glue Data Catalog. We'll talk about that. We added support for CloudFormation. We also added a bunch of other services also started putting the data in formats that Athena likes on top of data on S3. So for example, S3 Inventory just released a feature where they actually get their inventory details in ORC format on S3, and just you can quickly create tables on the data and visualize or analyze your S3 inventory. So since last year, we've had a lot of customers try us, and have given us a lot of great feedback. If you're in the audience, thank you very much. There are a lot of times when you've told us what you like and what you don't like about the service. As a new service, it's extremely important for us that you give us a lot of feedback. This has been a very, very interesting year. So we'll talk a lot about how these customers are using Athena. We have learned a lot more about the various use cases of how Athena is being used. Some that we aimed it for, some that we didn't. We've also integrated with several partners, especially the BI tools. You'll see some of the tools that you probably use in your day-to-day data analytics platform here. All right, so let's look at a bunch of use cases that we have seen since launch. The most predominant one is Athena being used as a query layer on a data lake. And that's pretty simple. What we've seen, if you talk to probably 100 customers that are building a data lake, they agree on one thing. They agree that S3 can be their data lake, and they would want to store the data in S3. They all disagree on how they want to access this data. You either run, a lot of them want to run Spark or open source applications on EMR. A lot of them run Redshift. They want to access the data out of Redshift. A lot of them want to run in a serverless manner like in Athena. So I think if you look at our serverless data analytics S3 data lake story, it's ingest everything into S3, and you have a lot of ingestion mechanisms that allow you to ingest the data. You have a common catalog that you can share across these downstream query engines, and then you have a wide variety of query engines to choose from on the downstream side as to how you want to access the data. So if you're just using SQL, Athena, Redshift, EMR are good choices. If you're doing Spark-based machine learning, EMR is a good choice, so on and so forth. So this is predominantly the biggest use case that we have seen, and when we look at our customers' use case today with OLX, this also kind of adheres to this pattern. The second one, which was very interesting, is we have seen customers, and especially SaaS providers, embed Athena as a SQL tool behind an API. and expose the data set that they have to external customers so that they can query the data directly. So, for example, in this case, Athena is sitting behind an API gateway, and it basically customers and all that SaaS provider has to do, or that application provider has to do, is push data into S3, and their customers can access the data using SQL. Also, it is a pretty cost-effective mechanism, right? Because all you're paying for in this case is the data that is on S3 for you to build a product out and expose it to the external environment. Athena is only charged on a per query basis, so unless somebody actually runs a query, you don't pay anything for Athena, you just pay on the S3 cost. So it is a very cost-effective mechanism if you're thinking about a product or if you're thinking about a mechanism to expose your raw data or your aggregated data to your end customers so they can run SQL analytics. So a good example is Timber.io. They're a startup. They basically do log aggregation and do log enrichment and allow you to quickly process your logs in a very easy fashion. This is their architecture, and they basically wrap their APIs around Athena. So if you look at the bottom layer, which is where they're collecting logs, they have a mechanism in which they collect logs. They take these logs, they push this into S3, they do some sort of ETL to push these logs into ORC formats, partition the data, and then they allow customers to query these logs. Now, they want customers to use a much simpler language than SQL, so what they do is they trap the query and decompose the query into multiple smaller Athena queries, and then directly talk to the Athena API. So essentially, their operational workload in this case becomes as good as putting data in the right format in S3, and as their customers grow, Athena scales along with them. Very interesting use case. The third one that we've seen is migration from on-premises Hadoop environments. And if you look at a typical on-premise Hadoop environment, you would see that there are a bunch of things that are going on there, right? So there is some ETL, either using Spark or Hive. There's some data wrangling that is going on. There's some machine learning with a bunch of open source tools. There's some interactive querying. There's some data science. And all of this is kind of centered around a Hive metastore that allows you to create a common metadata environment. So what customers are seeing is there is a wide variety of services on AWS that you can take your on-premise Hadoop implementation, you can break into those smaller components, and then deploy it on top of AWS. For example, you could use AWS Glue and Amazon EMR for your ETL. Glue is serverless. EMR allows you to do a high level of customization on the environment. You can use Athena, EMR, and Redshift for interactive querying. EMR carries a bunch of machine learning libraries along with it, so you can use that. But the common fundamental for all of these is that being able to use S3 as a data lake. You will see me repeating this diagram a lot, because it's essentially what we see as commonality across a lot of customers that are building the data lakes on top of AWS. So that's the third use case, which is migration from an on-premise cluster. The fourth one, which was very interesting, is AWS services by themselves produce a lot of service logs. And there is often a need to query these service logs to find useful information. For example, you might be querying CloudTrail logs for information that you want to dig out about, let's say, API access by a certain principal. Or you might be querying ELB logs, or you might be looking at AWS billing logs. So what we see is because these logs are automatically pushed onto S3, Athena becomes a really easy mechanism for querying these service logs. Typically, customers who are doing these are not the data analytics people in an organization. They are security engineers, people who are managing their network load balances, or people who have some kind of infrastructure that is on top of AWS. The architecture for this is fairly simple. Your logs gets deposited on S3. Sometimes it's in a format that Athena likes. Sometimes it might not be in a format that Athena likes. So most people use some sort of a Lambda-based transform to put this into the right format. And by right format, I mean in the right order or in the right layout of your data on S3. We'll talk about what is the right layout of data on S3. And then you allow Athena to be able to query this. A slightly more evolved version of this is that when you have lots of logs, for example, we have customers that would have several terabytes of CloudFront logs, and they want to go back in history and process those logs. They will take these logs and they will ETL it through Glue, convert it into columnar format, partition this, put it back into S3, and then it becomes available for people to query it using Athena. Now, the benefit of this is Athena has zero setup cost. That means when you create tables or when you put data in S3, Athena itself doesn't charge you. You get charged for the data in S3. That's different. But Athena doesn't charge you for creating tables, adding partitions. So we see a lot of customers doing like hundreds of DDL statements day over day. And then one day when they need to actually query this data, they can easily just go to the table, go to the Athena console or the JDBC interface and just query this data and get their results. So really good for ad hoc querying of this of logs, especially AWS service logs. So a lot of you gave us feedback that you guys generate these logs. These are all AWS service logs like CloudTrail and ELB and VPC flow logs. Why are you making me write all of these, create table statements to do all of these? Why don't you just create a very simple template that allows me to query these logs instantaneously on top of data in S3? So to do it pretty quickly, we started writing a bunch of blogs where we had CloudFormation templates and the most common queries that you would have pertaining to every service log. So for example, if you just search for AWS Big Data blog and click on Athena, you will find this blog which talks about visualizing AWS CloudTrail logs with Athena, Glue, and QuickSight. And it gives you the entire pipeline. You can launch this pipeline. And there are a lot more. For example, here's one that processes the cost and usage reports, also known as the billing reports on Athena. Here's one that takes a backup of DynamoDB data set and takes out and figures out what are the top N objects if you're looking at hotspots in your DynamoDB database. Here's one that actually looks at CloudFront. And the use case here is I want to look at bot activity from my CloudFront logs. So all of these blogs have, here's my create table statement. Here's what a CloudFront log looks like. If I want to run a query on this data set, here's what it'll take to run a query on this data set. If you want to do it one time, it's pretty simple. Create a table, run a query. Now, if you want to do it multiple times, maybe on an everyday basis and create a report out of it, then here's a pipeline that will allow you to do it in a much more structured and cost-effective manner. And it goes on to a lot of different things. For example, this is one on Aurora databases where you can query the log files for connection, query patterns, so on and so forth. VPC flow logs for detecting any kind of network activity, so on and so forth, right? So there's a lot of templates available out there for you to follow. The reason I put it out here was that if tomorrow you're in a situation where you need to go and look at S3 access logs, go to the blog, you will find a table creation statement there. You'll find some best practices of querying the data set, and it will be a pretty quick ramp-up curve for you to query those logs. We also saw customers like Airbnb use this as an underlying system to build completely new products. So for example, Airbnb has an open source project that's on Git called StreamAlert. And what StreamAlert does is it allows you to deploy an infrastructure that gives you real-time alerting based upon out of logs based upon the rules that you set. So it's a very simple, scalable, serverless environment. There is zero or very minimal infrastructure requirement for this. You can find it on GitHub today. You can easily deploy it to your infrastructure. It'll support a wide variety of data formats. It can take data from cloud, your data center, or other sources. It'll support data types like JSON, key value store, and key log, and also supports a variety of formats. And this is all open source. You can deploy it on your AWS environment. Here's an architecture, and the best way to kind of look at it is go from left to right. So on the left-hand side are all your producers. On the right-hand side, at the bottom is your rules engine, which is basically looking at real-time, processing those rules. And then all of this data goes and sits in S3. So if you want to query data that is not real-time, use Athena for doing that. And that uses the Athena APIs itself. So here's an example. In this example, we pulled the SQS queue for the latest S3 event-based notifications. Based upon what notifications are there, the context of what file is present in S3 is present in the notification. And based upon that, it spins up a Lambda function and updates a table or partition on top of Athena. It's fairly simple, but the architecture is pretty clean. So that's on querying AWS service logs, or essentially any kind of logs. You can extrapolate that theory to any kind of logs. The fifth one is an interesting one because we see a lot of people query database backups because either they want to query it for archival purposes, that they have a huge database, only 10% of it is actually used, and they want to keep the data set always queryable for compliance or historical reasons. They back this data up onto S3, and then Athena becomes a really good way. They have to set up tables once, and Athena becomes a really good way for querying those tables. There are blogs on how to do this for something like SQL Server or Oracle on the AWS Big Data blog as well. Also, we have seen customers push time series data onto S3 and then query and use Athena to query the time series data. Now, the one critical thing that we have seen in these for these customers is they are very latency tolerant. That means they're not looking at a real-time view of your time series data. If you were to get something that is more real-time out of your data store, then you probably want to use a NoSQL system with time series data. So Athena doesn't play in a good role there, right? The latency for a query in Athena is seconds, not milliseconds. For that, you have to use a NoSQL store or something like DynamoDB. For customers that are basically looking at time series data and they are tolerant to latency, or they're looking at large aggregations of this data, that data can directly land in something like Kinesis Firehose and pushed onto S3, and a Lambda function can be used to partition it. If you're hearing me speak the word partition a lot, we will go deep into what that means and how to set it up. We also added support for geospatial data, so you can build geometries on Athena. So if your data is in well-known JSON, and you can create data types and build relationships out of that geospatial data. This is fairly new. It's about 2 to 3 months, so we're very excited with how customers are going to use this. All right. So one question that we get pretty often is, how is Athena different from something like EMR or something like Redshift Spectrum? Essentially, what we're trying to do is we're trying to extend different use cases to double down on the whole idea of S3 being a data lake. So Redshift Spectrum is Redshift's way of extending that capability onto S3. So if you are a predominant Redshift user and you already have data in Redshift and you now want to run ad hoc queries on data on S3, Redshift Spectrum is a great use case. Athena runs Presto underneath. You don't interact with the Presto engine, but you interact with the Athena API. But if you wanted to run Presto on top of EMR because you want complete control over the cluster, you can do so as well. And all these three systems are essentially doubling down on the whole concept of S3 as a data lake, right? So for customers who are using EMR, that has always been the case, that they have access data from S3. Athena is essentially serverless, so if you don't want to manage your cluster, you want simplicity, go for Athena. If you're already a Redshift user and you're looking a way to ad hoc, to access data in S3 in an ad hoc manner, Redshift Spectrum is probably a good way to look at it. All right, there are 3 ways you can connect to Athena. When we started, we only had a JDBC driver, and what we realized was we thought Athena is like an ad hoc query tool, so people would like to just connect it using a JDBC driver. We were very surprised that how many people wanted to query it using an API, which told us that people wanted to build serverless, event-driven pipelines to offload reporting onto Athena. So we added an API. We also added a ODBC driver, and of course, you can use Athena on the console. Now, the API that we built, unlike the JDBC and ODBC driver, which is synchronous in nature, that means you send a query, you wait for the results, you get the results. The API is actually async. That means there are 2 key APIs there. There are also APIs for like listing query executions, listing results, listing query history, and so on and so forth, what you'd expect from any AWS service. But essentially, the 2 ones is you start query execution. That means you go and run a query, you get a query ID, then you pull on the query ID to get the results. So it kind of decouples the execution of the query and running the query. And we have seen a lot of customers use this with Lambda functions to do event-driven. I have some data that comes in, I spin up a Lambda function, I query the data, and I process, and I get the results. We have seen a lot of this in doing data quality checks before you're loading your data into some kind of a database or a data warehouse. There's a Lambda function spins up, runs creates a table, runs a query. You get the results. You see the results look fine. It's exactly the same number of records that you expected. You load the data up. Really good, easy use case for Athena. So let's talk a little bit about creating tables on Athena, right? Because essentially, if you look at the total, Athena deep dive is creating tables, creating partitions, and running queries. Essentially, those are the three things you can do on Athena. So databases are basically logical concepts. They don't have, it's a logical collection of tables. Now, when you start with Athena, like any other AWS service, there is a limit on the number of database and tables that you get in your basic account. Now, you can increase that. These are soft limits. You can increase that by going to a limit increase page and increasing and requesting us for a limit. So you can increase your databases, you can increase your tables, you can also increase the number of partitions. Now, Athena uses a combination of Hive to run your DTL queries, but it also uses Presto to run your SQL queries. But you don't interact with these systems. It does interact with the Athena API. There are many ways to create tables on Athena. First, you can go to the console, and you can directly write a Hive DDL statement. You can directly use the Athena API and give it a Hive DDL statement to create a table. You can use the JDBC and ODBC driver. But remember the diagram that I showed you, and there was a glue catalog in between Athena, Redshift Spectrum, and EMR. The reason the glue catalog is in between is because it's a shared metadata catalog that can share metadata between EMR cluster running Presto, Spark, or Hive, Redshift Spectrum, and Athena. So once I've created my table in any one of these systems, and if I'm using the glue data catalog, we'll talk a little bit about the glue data catalog, but once I've created a table, all of these three engines can actually see the table. Right? So that means I can also use Glue directly to create tables. That means I can directly call the Glue API to create a table, and Athena will be able to see those tables. Glue also has a concept of crawlers. Crawlers are essentially things that can run on your data in S3 and automatically infer schemas and create tables and automatically give you information about the data that you have already in S3. So it can automatically create a table, create a partition, so on and so forth. So you can use the group crawlers to crawl the data that is sitting in S3, create a table, and then Athena can query it. You can go to EMR using Hive, create a table, and Athena can query it, or vice versa. You can also use the Glue API. So if you are, for example, adding 1 million partitions a day, the best way to do it is directly calling the Glue API to load partitions. A lot of our customers come to us and say, we need higher rates, or we need higher rates of how we are running DTL queries on Athena. And the best way to do it is to use the Glue catalog and directly call the Glue API to add partitions or add tables, so on and so forth. Creating databases or creating tables is pretty simple. So Athena only works on the concept of external tables. That basically means that where your data definition or where your metadata is stored is different from where your data is stored. So for example, if you look at this create table statement, this create table statement must always have an S3 prefix at its end that denotes the location of where the data resides in the table. Now, in this case, Athena can only create tables on prefixes, and every object that you have in the prefix will become a part of that particular table. So in this case, for example, I have an S3 structure like this, my data logs, data 1, and I have a bunch of objects in there. If I want to create a table on this structure, I would create external table. I will give the location that maps to the prefix. So when I query this data, all the objects inside that prefix will get queried. That means in the next minute, if I added a new object and then ran a query, all the new objects will also get queried. So all the data inside a particular prefix gets queried. Also, when you create a statement like this, there is an Athena data catalog, which is basically very similar to a Hive metastore that stores this metadata. What does it store? It stores a table name, it stores the location, it stores what is the format of the data, it stores other things in, like statistics on the data, so on and so forth. And this you can share. We'll talk about that a little bit more. This differentiation of where the data lives and where the metadata lives is key to thinking about how you rightly think about Athena. Because Athena uses schema on read versus schema on write. So in a traditional database, you first define your schema, then you ETL the schema, and you load the data into the schema. And by the process of that, you prepare the data for the queries to become really, really fast. You also root out any inefficiencies in the data. For example, if you have an invalid column, or if you have a column that is null and you don't expect it to be null, then you root it out because you're loading the data into a database or into a data warehouse when you're doing schema on writes. That has its own advantages. Athena doesn't do that. Athena does schema on read because that's why it's really fast, that you can keep your data in S3, just create a schema on the data, and the schema is applied to the data when you are actually running the query. So for example, if I say that this table is CSV file, and I want to process each row as a regular expression, when I do a create table statement, nothing changes. No data is moved, no data is touched. It's basically just the metadata is created. Now when I run a query, that means in that query, every regex expression is run through every line of Athena, and it's evaluated that once. So the schema is applied on the data. Both have its advantages and disadvantages. I think schema and read is really good for exploration and for experimentation and for quickly getting your data or quickly creating tables on your data. These are various sets of formats and surveys that we support. A survey stands for a serializer, deserializer, which basically tells Athena what is the kind of underlying data that we have. So regex, grok is basically a regex pattern that can be named. So there are about 200 to 300 different grok patterns that you can find, which are predefined patterns for specific kind of files. So but they basically regex patterns, but they're named regex patterns. You can do JSON, you can do OpenCSV, TSV, and we also do columnar formats like Parquet and ORC. Athena is much faster when you're using columnar formats like ORC and Parquet. We also have data that is Avro and Geospatial. We also support a bunch of compression formats. I'll leave this for your reference. It's also in our docs as to which compression format actually gives you the best bang for the buck. Now, if you do compress your data, because Athena charges you by the amount of data scanned, your costs in Athena go down. That means even if I have to decompress the data to process the query, I will only charge you for the compressed data that is sitting on S3. So if I have a terabyte of data in text files, you converted this into Parquet, that probably became about 110 to 120 gigs. When you run a query on this data, I will only charge you for what the compressed data, even though I have decompressed to run the query. So we are encouraging you to compress the data and put it on S3, or to compress the data, because when I scan less data from S3, I become faster. Okay, let's talk a little bit about the Glue data catalog. So we talked about Athena uses an internal catalog called, which is called the data catalog. This catalog is the same catalog as the Glue data catalog, but with a bunch of features that we have added to it. And I'll talk about how do you upgrade from an Athena-based catalog to a Glue-based data catalog. So the catalog is a single view of your metadata. It allows you to classify data. It allows you to search through your metadata. And it also does things like schema versioning. It is a Hive Metastore compatible data store. That means you can hook it up to things like an Amazon EMR cluster running Hive on top of this data. Again, my favorite diagram is here. The purpose of showing you this diagram is what we think is the Glue data catalog is going to become the central metadata repository for all the data that sits on S3 and outside. So the Glue data catalog can crawl data from any JDBC source like Redshift or RDS or anything that is JDBC compliant and on S3. So it becomes a central metadata store for all your data. And then we have a bunch of downstream engines that are hooked up to the data catalog that allow you to query the data. So as I said, most of our customers agree that they want to use S3 as data lake. They disagree as to how they want to process the data. And this notion of a data catalog kind of unifies that view. So here's a view of the data catalog. You would see that it has recognized a bunch of files from Redshift, from SQL, CSV, Parquet, JSON, so on and so forth. So how do you populate your data catalog? You can populate your data catalog by a bunch of using crawlers or by directly using DDL statements, so on and so forth. When crawlers populate a table, they also give you a lot of information. For example, they give you table properties that you can extend with custom information. For example, you can add business annotation or business information about these table properties. They also give you statistics, for example, how many objects did I crawl, so on and so forth. And as we progress the data catalog, we will keep building more information on top of this. They also automatically infer schemas. When you run a crawler on the data, we can automatically infer the schema. So for example, in this case, we had a nested structure, which was a complex structure using the data type struct, and we were able to infer these schemas as well. We also automatically register partitions. The reason I say partitioning a lot, because downstream engines like Athena are able to reduce the amount of data you scan by using partitioning. So partitioning is just like using a virtual column with a where class. So most people are not querying all the data all the time. So by partitioning, you can restrict your query on a smaller data set and scan less data and then pay less and become faster. So glue crawlers can automatically do this. So glue crawlers can also give you versioning on your schema. So if your schema changes between day 1 and day 2, it will automatically create a new version of the schema and then gives you the ability to do what you need to do to deal with that mutation of the schema. You can run the glue crawler in an ad hoc manner. You can run it on an event. You can also schedule it. So it is a good way to keep your catalog up to date with the data that you have on S3. So how is glue crawler doing this? So at the core of a glue crawler is something called a classifier, which is basically a bunch of grok patterns that are put in an ordered format. And what it does is, when it looks at a particular data set, it gives me a number, a certainty number between 0 to 1, as to how certain it is that this particular data set is exactly how I read it, right? And based upon this, you can also add your own custom patterns. So for example, how does it do partitioning? What it does is, if you look at this partition hierarchy, I have a month and date. That means I partition by month and date. So I have date 10, date is 15. I can see that the schema on the files on date 10 is the same as the schema on the file that is date 15. And then based upon estimation on these classifiers, I can say, or the glue crawler can say, that this possibly is a partition. And that's how he loads up the partition. You can also write your own ordered set of classifiers as grok patterns to tell glue crawlers as how do I want to crawl my data, or what do I want to expect when I crawl my data if you have some different data sets. Now, this whole idea of is the catalog with Athena or is the catalog with glue can become quite confusing. The reason is because when Athena launched, the glue catalog was only internal to Athena. That means you can only access it with Athena, via Athena. So all the permissioning model to the glue catalog was via Athena. As we are expanding glue to new regions and building all these features in glue, we are also, you have an option to upgrade from the Athena catalog to the glue catalog. There is no data that moves. There is no metadata that moves. The only thing it changes is with the glue data catalog, it becomes a public API. And Athena stops authenticating any request to it. All the authentication or the permissioning model for glue catalog then becomes a glue, glue permissioning model. So with Athena and glue, if you have upgraded to the glue data catalog, you would have to have both permissions, Athena permissions and glue permissions. It gives you 2 levels of permissioning model on top of Athena. So a good way to think about this is, here was the world when I was on an Athena, an internal data catalog. The data catalog authorization was inside the purview of Athena. When I migrate, it becomes outside, and Athena becomes, the catalog becomes an external service that you can call directly by an API. That's when you can start hooking it up to things like EMR, Redshift Spectrum, and other data sources as well. So how do you upgrade? So upgrade is a very simple process. It's really not changing anything on the data or the metadata. It's basically saying that I can't have 2 authentication mechanisms to the same data set or the same metadata. So it's basically saying, from now onwards, I will stop honoring any glue-based access from Athena, and you must add glue policies to your Athena policies to keep accessing this data. So before you upgrade, you essentially have to modify your policies to add your glue policies, and you will be able to do that. You'll be able to use glue. So now we have one central metadata store per account. That means you don't want any IAM user to have the ability to just upgrade your data catalog to the glue catalog. So we built a new API called glue import catalog to glue. And you basically need permissions to this API to be able to upgrade. What that does is it intentionally allows an admin to go and upgrade it, because once you upgrade from the glue data catalog to the Athena data catalog, you upgrade it for an entire account. So for example, if I have queries that were running on Athena and it had no glue permissions, and suddenly somebody went and upgraded the Athena data catalog to the glue data catalog, exactly the same thing, no change in data, no change in internal. That means my queries, Athena will stop authenticating. That means Athena queries will fail. So the way to do it is go and add glue policies to your Athena policies, create a permissioning model for this API, and then upgrade to the glue catalog. Lots of benefits of upgrading. You can use crawlers. You can share metadata between EMR and Athena and Hive, Spark, and Presto that is running on EMR. You can also run then the glue API directly if you want to run high concurrency DDL statements. So instead of doing alter table add partition, you can just do partitioning. So let's talk a little bit about partitioning your data. So what partitioning does is, partitioning allows you to read only the data that your query needs. Essentially, partitioning is a virtual column. You define partitioning at the time of defining a table. And then in your where class, you will be able to use different filters. And based upon different filters, I might not read all the data. I might read only a small chunk of this data. You define partitions at the time of creating the tables. Athena uses Hive-based partitioning. But especially if your data is text-based, that means text is not really a good format for querying data. For text-based data, I have to read the entire data set to be able to go to a particular column. That's not the case with columnar data formats like ORC and Parquet. So if you're really using text-based data, then partitioning gives you a lot of really good advantages. And I'll show you some examples. So here's an example of the same query. It's about on 74 gigs of data. So on the left-hand side, I have a query. The first query is just giving a ship date or just asking me information about a particular ship date. It takes me about 9 seconds because on the non-partition table, because the table is not partitioned, and it scans the entire table. When I partition the table, it is several order of magnitude cheaper, because what then I do is I don't look at anything else. I would just look at that ship date and go and process data in that ship date. The second example is a range of partitions. So I want to get data between these 3 partitions. And you can see that in the first case, it takes me about 10 seconds on a non-partition table, but it takes me really, really less, 2.73. And you can see that the data scan. In the first one, I'm scanning the entire table, 74 GB of data. In the second one, I'm scanning some 800 megs of data. So it is infinitely faster to partition the data. And partitioning of data only means how you lay out your data in S3. So let's talk a little bit about that. Also, partitioning has a little bit of an overhead. That means if you're always going to scan your entire table, probably partitioning is not a great use case for you. Because I do spend some time fetching all the partitions and finding out the partition that you need to go to, right? So I talked about partitioning as a way that partitioning is defined at the time of defining a table. So in this case, imagine I have a table, and I want to partition it by 2 things. I want to partition it by year and month. The way I want to use this, the way I would lay out my data on S3 is, this is the path to my basic table. This is my partition column 1. This is my partition column 2. And this is how my data, possibly, there are other variations that I'll talk about, but this is how my data should be laid out in S3. So now, when you actually use the SQL query and say, where is year is equal to 2015, month is equal to 11, it has a unique S3 location associated with that tuple. And it only goes into that S3 location and queries the files that are in that S3 location. That's how we're able to scan much less data. That's why in previous diagrams, you see a lot of people using Lambda functions, Because what they're trying to do is data comes in one prefix, they're trying to take a Lambda function and put it in a partition format so that when they have to query 1 day's worth of data, they're not querying a year's worth of data. So here's an example of how this might exactly look like. S3, your bucket, your table name, year is 2017, month is 11. Now, before you can use partition, you also have to tell the data catalog where is this partition. So first, you have to define that you want the partition, which is in your create table statement. You have to lay out the data in S3. You have to also tell me, using a DDL statement, that where is this partition. The way I do it is using an alter table command. So I can do something like alter table access log, which is the name of my table, add partition, and then I give each partition a value, and then associate that value with an S3 path. Now, it doesn't need to be 2 levels of partitioning. You can have any level of partitioning that you want, single level, 6 levels. But essentially what it is doing is, with that unique keys or combination of keys, it is associating an S3 namespace or an S3 path to that keys. So when I use in a query, give me so-and-so where year is 2017 and month is 11, it understands that this query is only going to that partition, and it goes and scans only that partition. Right? You can do that directly. Now, you can do this alter table directly with the Glue API. You can also do it using an alter table command. I'll talk a little bit about this. But what if my data is like this, right? 2017, 11. It doesn't have, how do I go back? Yeah, it doesn't have year is equal to 2017 and month is equal to 11. What if it doesn't have this? That doesn't matter. In fact, you can still, the key or what is the value that you're going to reference that data with, you are still specifying that key. It's the same way as, remember, my pointer, here we go. So it's the same way, year is 2017, month is 11, and it goes through a unique S3 location. It doesn't matter what the location is called. In fact, if you look at the last, so there's also a command called MSCK repair table. So if your data is actually in this format, which a lot of people who have used Hive before, that means it has its key and a value on the S3 path. You can just use this command called MSCK repair table, and it'll automatically load all your partitions. This is a pretty expensive command because it actually goes through all your S3 namespace and validates all your partitions. So if you're just loading one partition, don't use this because it will scan all your partitions all the time, right? So, but if your data is in this format and you are like if you have a lot of Hive data that is sitting on S3 and you want to immediately load all of that data into Athena, you can do an MSCK repair table and all the partitions will be loaded. The second is if I have data in this format and I can do alter table, add partition, I can give it the values and an access location. I can do about 99 of this in the same alter table command. And what it means is you can actually do it anytime you want. The data doesn't need to be present in that S3 namespace. It is basically associating a key value, a unique set of keys to an S3 location. So for example, I can even do this, right? So for let's say my bucket, because a lot of people will tell me that, look, if I use these namespaces and these names in my buckets, then it doesn't follow S3's best practices, which are to introduce entropy in your prefix name, in your prefixes and object names. So for example, if you use a bucket like this, I do exactly the same thing. Alter table, year is 2017, month is this, and path to table and this. This should also, this will also work. This is all you need to know about partitioning. Now, when you do, there are many ways of loading partitions. You can use Lambda, you can use MSCK, you can use alter table, you can do over 99 of them in the same thing. As I said, a lot of people, to add the daily partitions, they would go and do it at the start of the day. You can also schedule a crawler to run it automatically, or you can directly call the Glue API using an SDK of your choice to do something. Now, the way you choose your partitions is also important, right? Partitions are nested. That means you can use one or multiple columns as partitions. So that means you can use, instead of using a date, you can use year, month, day, and then you might have a customer ID. But you want to choose your partitions in such a way that your partitions are roughly balanced, and each one of them has roughly an order of 128 megs of data when you look at all the partitions. Because beyond that, you are spending a lot more time actually getting and fetching the partition than actually going and running a process, right? So look at your query patterns and define your partitioning in a way that you think that if you're running a query on all your on your data for an entire day every day, then a date-based partitioning makes sense. If you're running your partitions across a customer, that for this customer, I need to run a query every day, then you probably make sense to do your partitions again. Remember, you can change this. A lot of our customers do change partitions as well. Because essentially, remember metadata? This is all that it's doing is there is a metadata string that says, if you give me a where clause with these 3 partition keys, I will go to this particular location. So you can change that as well. So let's look at a couple of other things when you run queries on Athena and how can you improve performance. First of all, Athena doesn't like small files. I think most big data systems don't like small files. It's a reality of our life that most data is produced in small files. That's true, right? So it's very easy for me to stand up here and say that don't use small files, but I understand. I've gone through the pain of hearing you tell me that my file comes in KBs because I have an IoT device there that sends data using Firehose and it dumps it in S3. But here is an example of the same data set. On the top, it is split across 5,000 files, and at the bottom is just one file. You can see how different the performance looks. What we have seen people do is people use Glue to aggregate the data and create hourly aggregations if the files are really small. So concatenate your data and expose that data set on top of Athena, and your querying will be much faster. When you convert your data into ORC and Parquet formats, in this example, we're only using Parquet, and Parquet is a columnar format, we run much faster. We run much faster because the data is compressed. And with ORC and Parquet, which are columnar format, not only can I select only the columns that you reference in the query, I can also go and get much better at finding the data that you want. So for example, this same data set, 1.15 terabyte in text, when I convert into Parquet using the standard compression that Parquet uses, gets me about 130 GB, so lower S3 footprint as well. And if I ran a query on the entire data set, the one that took 236 seconds and costed me about $5, takes about 6 seconds on Parquet and costs me multiple fractions lower. Order by clauses. If you are using order by clauses, a limit clause on the order by clauses will significantly improve your performance. Most of the times we see customers using order by and they're only looking for top 10. So if you add a limit to the order by clause, I think it will be significantly faster. Joins. There's one trick to doing joins, which is if you keep your larger table on the left-hand side of the joint, such as the example that is given here. So on the part table is actually the bigger table, and the line item is actually the smaller table. If you just reorder those things from the left to the right, your queries start to become much faster. Also, because people process a lot of JSON-based data, there's also a lot of like operators people use. You can also regex-based operators are much better than like-based operators. You will see some 20 to 25% performance improvement on those. All of these are documented on a blog, right? So you can look through that. Last, a bunch of things that are coming soon that we are launching in the next couple of months. So if you run into a query resources exhausted error, we're basically solving that problem in the next couple of months. What it's doing is today Presto doesn't have an ability to spill to disk on large aggregations. It does all its analysis in memory. And with Athena, it's able to just with Athena, we're adding functionality that it will be able to spill to disk. So you'll be able to do aggregations on really large data sets as well. We're also adding a new optimized Parquet reader that improves performance, especially with complex data types. We are adding a lot more on simplified error messaging. So if you have used Athena and you've gotten an internal error, we are doing a lot better with those error messaging. We will tell you exactly what the error is and what is the remedial action. We chose not to add logs to Athena because essentially what we want to do is give you a remedial action of what you can do with Athena. Also, we wanted to keep only a single version of Athena so that you don't have to upgrade from version X to version Y of Athena. So all upgrades on Athena are transparent. We are very soon upgrading to a version of Presto that is based on version 1.7.2. But you won't need to change anything. Your queries just run exactly the same. They run faster. But there is no upgrade requirement for you. All the upgrade happens automatically. With this, I'd like to invite Raul to help us talk through the OLX case study.
Can you hear me? Can you hear me? Okay, nice to meet you all. My name is Renteria. I had the big data team at OLX Brazil. I will give you a short overview of our experience with Athena throughout, I guess, the last year when we implemented it. So I will do that in three thoughts. So first, I will give you context, why we use it. Second, how we did it, how we implement that stuff. And finally, I would like to give you some advice, some stuff that we learned over since January when we implemented it. Okay, first, to give you some context, who you are. We are the biggest online marketplace in Brazil. Every day, millions of Brazilians, they come to our platform and they go there to buy or sell their used stuff, from pencils to apartments. So we are located in Rio de Janeiro. As you can see in that beautiful picture, we are near the Bay Area there. And we are part of two world leaders in online marketplace, namely Schibsted and Naspers. To give you a perspective of the size of the business and how it's growing, just some numbers. Every month we have 700,000 people coming in and publishing content for the first time. And to give you an idea also, last year, 2016, we had 1/5 of all the cars sales through the platform in Brazil, right? Continuing on the contact side. So back December last year, where we were on the data platform that we had. As you can see, we have the acquisition of the different data sources on the left. On the bottom, you have the data warehouse, where most of the load was at that time, and it still is. So many visualization, many ad hoc queries, a lot of exploration going on there from all different departments of the company, right? It's not about only devs, engineering, and product. On the top, you see that we have our data lake. The data lake at that time was being used mostly by the data scientists and a small group of data analysts. To give you an idea of the load that we have at that time, we had ingested every day 0.2 terabytes and every day 50 terabytes consumed. As I explained to you, we serve the whole company, every type of user in the company. That's something that we want to push and we keep pushing. And so different users will load and scan the data, the same data, and aggregate it in different ways. That's why you see that huge difference between ingestion and consumption. Okay, one key message in that architecture is that we construct something that was available for everyone in the company to use with this different set of tools in aggregation, in data aggregation, the way that better fitted their jobs, okay? That's the philosophy behind this architecture. Going on the context, so to give you a good, explain the story. At that time, December last year, we were observing a high user demand. Not only the number of users and employees were, we were observing a 20% increase year over year, and that's still the case. And we also had a clear push from the company. We want every department to use the data to help them make better decisions. So data must be part of the decision-making process. So that's something that we push a lot. That's also part of the goal of my department. And at the same time, as you can see on the bottom here, we had some very data-savvy projects in the pipeline. Like we were developing a new messaging service. We also were expanding the coverage of our user tracking devices, and mostly we were developing some machine learning basic user profile mechanism, so we would better understand how content is created in our platform, and also implementing recommendations through collaborative filtering. So what we did, so that was December last year, and that was in January, so 1 month later, we did two things. We removed the load on the data warehouse, and we removed Presto from the picture, from the architecture, and we put Athena directly there on top of S3, serving not only the ad hoc queries, but all the data products processes that we had. So that was the move that we did. In a short, we put that query engine on top of the data lake and served everybody in the company. So, and going and giving you so a bit about talking about the timing. So Athena was launched by Abhishek exactly at the same time that we were observing that huge demand, and we were foreseeing a lot of demand going on throughout the year. And so we decided to take it, and we implement that stuff in 2 days. That was done by January 2017. 2 days, given the fact that we formatted the data in S3 using some guidelines. Okay, I will show you that in a short. How we implemented that, so give you a bit more details here. So if you look at our data architecture, we have 2 clusters, one which is batch-oriented, a Spark, that loads data from the transactional and the external APIs. And we have another cluster that handles all the streaming-based jobs, okay? So those 2 pipelines, they will acquire all the data, process it, ingest directly into S3. And for observing performance gains downstream, it was important to do what I show you there. First, we had to put that in column form. I hope that at this point, by all the stuff that Abhishek told you, you understand that this was a key thing to do. Second, we partitioned the data. Again, that was very important. We use year, month, and day. Third, we use compression. That's very important to also use. And fourth, during the tuning process, we found out that it was better to keep the file size between 200 megabytes and 800. That was very important to get a good performance, right? And once we had this data formatted in this way, in the data lake, we were able to plug in Athena, and we had to do some tweaking there. We had to raise the number of concurrent queries and also the maximum memory available for the data querying. That's something that we worked with Abhishek. He helped us to make it through. And also, we also had to create a job, a batch job, to get all these tiny, smaller stream files and put them together using the file size constraint that I just explained to you. If you look at this story, this picture, it's clear that most of the job was doing preparing the data, right? And plugging in Athena was pretty straightforward. And what we managed to do that, so as I told you, we managed to do that in 2 days. The quality of the serving was good, very good. We managed to keep all users going on with their exploratory and all the ad hoc analysis, all that stuff kept going on. We also kept all the data products like the messaging, etc., all the stuff that I told you about. And also, as you know, as part of any technical decision, you have also to look at other alternatives. So what we looked at that time. So because timing was an important thing. As you know, every project time is a key thing to look at. So we had two things that we thought about. First, we could have implemented that ourselves. We could have taken open source like Presto and put that in place. But we didn't have the resource. I will have to expand the team. And I didn't have the resource/time to do that. As you can see on the right, if we look at the data ingested and consumed from December last year until last month, October, the daily rate grew by 10 times. If you look at consumption, just to give you a rough idea, it came from 50 terabytes to 600 terabytes in less than 1 year. And we knew about that. So that's why we need to be fast. So in that way, growing my team was not an option. Second, we could have used the existing data warehouse, right? We could have scaled it. But that will not be very efficient. We will be using the wrong tool for the job, and will cost us around $100K per month. So that's why we were able to put that tool in place and keep things going smoothly. So that gives you, as I told you, a short overview, right? Give you the story behind our implementation of Athena. I would also like to show you what happened after, right? Because that was done January. So as you can see on the bottom part, it's almost the same. We kept the DW as it is, but we just add a new layer for the marketing folks. But on the upper side, you can see that we brought back Presto. And why was that? As I told you, we have this this philosophy, this policy, that we want every department to be able to access data. So I'm talking every sales, marketing, everyone should access the data to enhance their decision-making process. And not everyone write nice SQL queries. That's the truth, and it's part of the business. And what happens that some group of users, they start creating very non-effective queries. So we start to see queries that were scanning unnecessary data, and as you scan unnecessary data, you create unnecessary costs. And that go out of our control. And for that reason, we had to put in place a more constrained environment where we could observe and constrain the resourcing on the query side. And we came back with Presto throughout the year, and that allowed us for some group. We still use Athena for data-oriented process. We still use Athena for some querying, but when we know who's doing that. Okay, so that's an important thing that we learned throughout the road. Looking at the whole thing, things to consider if you're going down, depending on where you are and that in your project. First thing, take a look at your data format on S3. Do that from the beginning. I don't think it will only help you with Athena, but also many other aspects of your data architecture. That's the first thing. Second one, very important, take a look at your data size and your team size. If you still at a smaller size on the data, I don't think that most of the stuff that I told you about today will be very relevant. And also, if you have a smaller team of people that know how to craft good SQL queries, so if in your company it's a smaller team that does that job, you won't face the issues that we had. You will be able to go easily throughout. But if you're in a larger environment where you need to provide exploratory and ad hoc analysis and reporting to a diverse group of users, then you will need a more constrained environment. And I mean by that two things. On one side, you will need to track how much resource you're consuming, right, on the querying side. And second, you need also to track the quality of the query if users are waiting too much to get the result back. So we'll need an environment, that's what we did with Presto, to watch and track those two things. And that's how we managed to, that's how we are today, as I told you. If you want to know a bit more about us, you have our direction there, the LinkedIn. Also like to thank two folks that helped to put that stuff together, Marcello and Hudson. And finally, I would like to give you a big thank you for your time today.